Alright, so now let's talk about pressurized vessels. The pressurized vessels would be translated to 압력 용기. So 압력밥솥 would be one good example of 압력 용기. So what kind of pressurized vessels that we can handle in our actual practice? For example, gas line pipe, or the liquefied natural gas storage, or milk tank, for example. Yeah, there are many examples. And also in these cases, the pressure inside is greater than the pressure outside. But also let's talk about submarines. In the case of submarines, the pressure outside is greater than the pressure inside, isn't it? Okay, the first one is the spherical pressurized vessel. We can find such kind of structure if you visit Incheon or if you visit Yeosu. Okay. Here for a kind of simplification, so we don't want to consider the effect of gravity, because we don't consider the effect of gravity, the pressure inside would be constant. So what's going to happen if you consider the effect of the gravity? Then in the vertical direction, on top of the tank, we have P naught here, and then because of gravity, the pressure increases by the depth of the spherical vessel, isn't it? So in this case, the problem is more complicated than the reference case. So in this reference problem in our textbook, we don't want to consider the effect of gravity. Okay, so let's say we don't want to consider gravity because there's no gravity, and then if you cut this spherical vessel in half, then there must be force equilibrium. The first component is what? The integration of the pressure over the cross-sectional area, and then what I mean inner cross-sectional area occupied by the substance, and then it should be equal to the integration of the stress, normal stress acting on the plate or the shell of this pressurized vessel, and then we need to integrate over the thickness and then the perimeter, over the thickness and over the perimeter, isn't it? Okay, so here actually this quantity, calculation of this quantity is pretty obvious, because here we introduce introduce no gravity condition. The pressure is constant. So once we know the cross-sectional area, inner area of the vessel, then we can calculate it very easily. Let's say this is inner diameter, the inner diameter and the outer diameter. And then this quantity is very simple. The pressure times the cross-section area, the inner cross-section area, the I squared, isn't it? The problem is this guy. Okay, so let's imagine D naught is much greater than the inner diameter. Then because of such a big difference, then maybe if you consider infinitely large diameter, outer diameter, then maybe probably here the stress-free condition, isn't it? And then stress condition would be maximum here because it's subjected to pressure, the inner pressure. Which means if you monitor the change of stress from the inner surface to outer surface, probably it would be maximum here, and then it would change like this, isn't it? So basically the normal stress is not constant in the thickness direction. But here we'd like to use the concept of plane stress, okay, the plane stress, which means if you introduce that simplification, the normal stress in the thickness direction is constant. This is our simplifications. So here what we want to do is, instead of this nonlinear distribution, so we want to consider the normal stress is constant over the thickness. Okay, this is our simplification. So because of this simplification, so we can take it out here. Okay, So our calculation becomes much simpler. And then another kind is the cylindrical pressurized vessel. So what you can do is we can imagine a spherical pressurized vessel, and then here we'd like to put a cylinder here. Then we can have the cylindrical pressurized vessel. Then again it's same. The pressure inside is constant, and then this is in equilibrium by the membrane action. So in the cross-section direction, and then also the longitudinal direction. So in this case, we have to consider the force equilibrium in these two different directions. But in the case of spherical vessel, because this is axisymmetric, so the condition is same in any directions, isn't it, right? And then this example is what happened in the submarine problem. Submarine. As I told you, the pressure outside is greater than the pressure inside because this is submarine. The crews are inside. That's why the pressure inside should be much smaller than pressure outside. So we have various problems. Alright, so now let's talk about what happened in the spherical pressurized vessel. So in our textbook, we'd like to introduce one more condition. This is a thin walled, and then the radius to thickness is greater than 10. This is a thin walled condition. Because of the thin walled condition, the membrane action can be calculated by this simplification. Normal stress times 2 pi r. 2 pi r is the perimeter, isn't it, right? Just perimeter times the thickness, and then the normal stress, the constant normal stress. So if you let them equal to each other, then we can calculate the membrane normal stress very easily. So a half and the thickness ratio, the radius to thickness ratio, and then the pressure. This is very simple. But how come we can use this simplification instead of the area calculation? So here let's talk about how come we get this simplification. A little bit more about it. So let's consider not that small, not that thin spherical vessel. So we have the finite difference, the inner diameter, and then outer diameter. Let's say I want to calculate the cross-section area here. The force caused by normal stress is what? The normal stress is normal stress sigma times the cross-section area of the hatched one. Okay, that's why we need to calculate the area of hatched part. The area of hatched part is pi over 4, and then we have two different areas, the outer areas minus, and we need to subtract the inner areas. First, I want to choose the outer diameter as the reference diameter, D. Then how do you represent inner diameter? Inner diameter is what? The reference diameter minus 2 times of the thickness. Oh, by the way, sorry, I forgot the thickness. Thickness T. Okay? So let's rewrite this equation using this reference diameter here. Then I have the square, because now I'm taking outer diameter as a reference one. In practice, typically we use outer diameter as a reference one, okay? And the minus, and then d minus 2t square. So let's take d square. Let's take out pi over 4, d square, the 1 minus, and then 1 minus 2t over d square. Okay, now let's introduce a simplification using the fact that the diameter is much greater than the t. Then if you use the simplification, then maybe t over d, as the first simplification, t over d is equal to 0. Then what's going to happen? If t over d is equal to 0, then 1 minus 1 is also equal to 0. and then this is equal to 0. So we cannot accept this simplification, which means we need to tune the simplification procedure a little bit, carefully. So before doing that, and what we want to do, we'd like to expand, that expression, the pi over 4 t square 1 minus, and then I'd like to expand it 1 plus 1 minus 4 t over t plus 4 t over t square. Okay, so look at this. So I have t over t is small, but I have square of a small one, but this is extremely small. That's why I'd like to drop the last term only. So if you do that, then 1 minus 1 is, this is cancels, and the 4 is cancels, and then square is cancels. So finally we have pi over t times the thickness. Is it clear, right? That's why we have this equation. Okay. Then what happened if you choose the inner diameter as a reference diameter? The conclusion is that the answer is the same. So you may want to try in your place. Alright, here we'd like to talk about the stress condition, the outer surface and the inner surface. And here what we want to see is, because this is actually symmetric, so if you choose a material point, if you choose a material point, the membrane normal stress is same in any direction, okay? Same in any direction. But here we'd like to see two different points. For example, the inner surface, it is subjected to pressure. The outer surface, in the decrease direction, no pressure. So which means if you check stress condition at point A and point B, then we're gonna have different stress conditions. So here, let me introduce new page. How can I do it here? Okay. And then let's turn around the page. Okay. So here, what I want to do is I want to consider these two different points. So point A and point B. So let's consider point A first. So point A here, and then I want to use this coordinate system, x and y and z direction. Okay, we just calculated the stress. My normal stress sigma is equal to a half of r over t and the pressure. And then also stress in this direction is same. Sigma is a half of r over t and the pressure. Okay. And then the stress in x direction is equal to 0. And then this is what's happening at point A. And then let's check point B. If you look at the point B, so we have same membrane normal stress, but here we have compressive stress in x direction because of point B is subjected to pressure P. The stress state is different. So let's consider a specific problem here. For simplification, we want to consider the pressure is, for example, 10 megapascal, and then R over T is equal to 10. Then how much is it? So this is 50, isn't it right? So I'll have 10 times 10 is 50, and then the pressure is 10. So in the case of problem A, and the sigma xx is equal to what? Sigma xx is equal to 0, and the sigma yy is equal to what? 50. And the sigma zz is equal to 0. In the case of point B, the sigma xx is equal to minus 10, sigma yy is equal to 50, sigma zz is equal to sigma xx, sigma yy zz is 50, sorry about it here, sigma zz is 50. Okay, so using this condition, I'd like to construct a Mohr circle to investigate the characteristics of the stress condition. So first, let's talk about directly let's talk about point B here. Okay, and then to construct a Mohr circle, so because the Mohr circle is two-dimensional problem. Okay, this is a three-dimensional stress condition. That's why we need to go one by one. X and Y and Z. So first, let's talk about the stress condition for X and Y. In X and Y plane, so we need to consider sigma X and sigma Y. Sigma X, this is minus 10. And then sigma Y, we have 50. And then first, and the second, so we want to consider what happened to YZ plane. The YZ plane, sigma Y is 50. And then Z is 50. This is biaxial condition. Okay? And then let's check what's happening in ZX direction. In ZX direction, sigma Z is 50. And then this is minus 10. 10, okay, 10. So let's try to construct a Mohr circle. This is 10, okay, minus 10. Let's try to construct a Mohr circle. Okay, so I build a spreadsheet, and then here the first I'd like to talk about XY plane first, and then sigma XX was equal to minus 10, and then sigma YY was equal to 50. Then we can calculate the mean stress and the stress difference and the cosine and sine, and then I can obtain a Mohr circle. Okay. And then here, okay. And the second one, the YZ plane, we have 50 and 50. 50 and 50. This is the biaxial condition. The Mohr circle is condensed into this one point, single point. And then third one is what? In Z direction 50, and then in the vertical direction minus 10. So this is the third Mohr circle. So here, if we work for this problem, so we have apparently we have only one Mohr circle. The two Mohr circles are duplicated, and the second Mohr circle is condensed to this point. This is what's happening. This is how we use the Mohr circle to investigate the stress state. What would be the maximum shear stress here? The maximum shear stress is, look at the radius, the maximum radius of the Mohr circle. This is the maximum shear stress. Maximum shear stress is 30 megapascal in this problem. The next subject is a cylindrical pressurized vessel. In the case of cylindrical pressurized vessels, we have to consider force equilibrium two different directions. The first one, we have to consider force equilibrium in the longitudinal direction, And then also we need to consider force equilibrium in plane direction. So let's consider a small segment here. So if you consider small segment, this is here, as I told you, we can consider two different kinds of force equilibrium. So this one is very similar to what we discussed for the spherical vessel. That's why the pressure value is exactly same as before. And then if you apply the pressure, the equilibrium for this, so we have two different, the areas here on top and bottoms. Let's apply the force equilibrium. Then we can obtain the stress value as given here. Again, we'd like to consider the similar problem here. Let's say R over T is equal to 10, and then the pressure is equal to, let's say pressure is equal to 10 megapascal, similar to this. And the sigma 1 is equal to here, the 100 megapascal, and the sigma 2 is 50, okay? So as we did before, we want to consider point A and point B. So let's consider the point contact to the internal surface, and then this subject to pressure too. So let's simplify the problem like this. Okay, then here it is subjected to the sigma 1 first. This is sigma 1, and then in that direction it is subjected to sigma 2. Okay, sigma 1 is 100 and sigma 2 is 50, and then the surface is subjected to pressure. P is 10 megapascal. So here, to investigate this problem, let's introduce a coordinate system: x, y, and z. Okay, so first, to the Mohr circle, let's work for the x, y plane, the x and the y, x, y plane. In x direction, we have sigma 2. Sigma 2 is equal to 50. In the y direction, and how much is it? In y direction, sigma 1 is 100. Okay, and then the second one, so yz plane. Let's work for yz plane. Sigma y is equal to sigma 1 is 100. Yz plane is 100. In z direction, this is subjected to pressure. This is minus 10. And then finally, let's work for zx plane. Z is equal to minus 10, and then sigma x is equal to sigma 2, 50. Okay, so we are ready for the investigation using the Mohr circle. So let's try to build the Mohr circle. Okay, let me activate my Excel spreadsheet here. The first, for xy, sigma x was 50, and then sigma y is 100. Okay, then this is my new Mohr circle. And then for the second one, let's work for yz plane. Then sigma y is 100, sigma z is equal to minus 10, because this is the pressure. And then let's work for the third one. Sigma z is equal to minus 10, and then sigma x is 50. So finally here, so in these problems, we have well connected three different Mohr circles, isn't it? So then what is the maximum shear stress developed in this problem at this point subjected to contact into the internal substance? So here we can find the maximum shear stress is around 50 something, isn't it, right? The maximum radius of the Mohr circle. This is how we use Mohr circle to investigate three-dimensional stress state. Okay? And then here, before we talk about the example problem, let's talk about two different fabrication procedures to produce pipe. The first one is the helical welding procedure. The second one is UOE welding procedure. In the case of helical welding procedure, they wound the plate, in the helical directions. That because of this procedure, we have welding line. Okay. And in the case of UOE procedure, so we, first we use a long plate, and then we weld them together. That's why in second procedure we have a welding line, the straight welding line here. So usually the welding line would include some defect. That's why it is very important to check the stress development in welding line. Okay. So in classroom, I already discussed how to solve this problem. Okay, the key point this problem is first we calculate the normal stress sigma 1 and sigma 2 using that equation that we discussed of a cylindrical vessel. So once we have these values, what you have to do is we have to investigate the development of normal stress and shear stress in this welding line direction, because the angle is 35 in Mohr circle. In Mohr circle, by the way, I didn't show you my lecture. Sorry about it. So first we so I talked about two different the procedure of the pipeline producing the helical welding and longitudinal welding. And then in this example problem, so first we need to calculate normal stress, these two normal stresses using this equation that we discussed before. And once we have that, and then the next step is we have to use the Mohr circle. Look at this. The welding line is inclined by angle 35 degrees. In the Mohr circle space, we need to consider 2 times of it, so 70 degrees. Okay. So first you calculate sigma 1 and sigma 2, and then you construct the Mohr circles, the 3 different Mohr circles. This is 3-dimensional problems. And then you investigate, you calculate the normal stress and shear stress using the Mohr circle. Or if you don't like that, you can use a stress transformation formula. Your result should be exactly same as before. Okay. So let me stop my lecture here.